In previous videos, we've learned how graphical models like position versus time and velocity versus time graphs and motion maps can help us to graphically model motion. In this video, we're going to take a little more detailed look at algebraic models for constant velocity particle model of motion. We'll learn how to translate from graphical and verbal models to algebraic models, and then how to use algebraic models to solve two specific kinds of problems that we can be faced with in constant velocity particle model of motion. First, let's review the basic line form of the constant velocity particle model of motion. The position x at any time, t, is equal to the starting position plus the velocity multiplied by that time. It's just the equation of this line that represents motion in the constant velocity framework. Let's translate a couple of position versus time graphs to algebraic models. First, we'll find the starting position by just reading the vertical intercept. In this case, it's 12 kilometers. Then we pick 2 points on the line and look at the change in position, or displacement. In this case, it's 90 kilometers. Then we look at the change in time, which in this case is 45 minutes. The ratio of displacement to change in time is the slope, which is the velocity. In this case, that's 90 kilometers over 45 minutes, or 2 kilometers per second. Last, we just fit the starting position and velocity into the form of the CVPM equation. Let's do another one. Here, the starting position is 96 kilometers. The displacement here is negative because the position is decreasing over time. And that's going to make the velocity also negative. So when we calculate this, it's 96 negative kilometers over 48 minutes, not 45 minutes. Read that wrong. And we get a negative 2 kilometers per meter. This is per minute. So there's our final equation. And the plus a negative 2 could be replaced by just minus 2, 96 kilometers minus 2 kilometers per minute times time. We don't need to build a graphical model before we build an algebraic model. If we have a description, we can often get the information we need straight from there. If we know the object is moving at a constant speed, for example, we know that we can use the form position is starting position plus velocity times time. If we have information about where the object is at the start of the motion, well, that's our x0, or beginning position value. In this case, 2 meters. If we don't, we can assume that's 0 and just at least find a change in position. If we know the direction of motion, then we know the sign on velocity. In this case, it's positive because the object is moving forward. The size of the velocity is the speed, and when we put that all together, we now have the equation. So to review, we look for starting position from the story. The direction of motion is the sign on velocity, and the speed is the size of the velocity. And then we have the equation. Let's do this in reverse. What's the motion that's modeled by this equation? Well, we know that it's moving at constant speed because of the linear equation. We know that it started at a position of 50 meters. The negative sign on velocity means it's moving backwards. And the size of the velocity tells us that its speed is 10 meters per second. We can also translate from a motion map to an equation. In this example, because the dots are equally spaced and the velocity vectors are equal lengths, we know that it's moving at constant speed. Because the first dot is at 2 meters, we know the starting position. Because the velocity vectors all point in the positive direction, we know it's moving forward. And because the dots are 2 meters apart, we know that it's moving 2 meters every second. So the speed is 2 meters per second. Putting all this together, this allows us to build the equation. The position is the starting position, which we know is 2 meters from the map, plus 2 meters per second times the time. Let's take a look at two common problems that a CVPM equation can help us solve. One thing we can do is use the equation to predict where an object will be at a certain time. This is a common problem. So here we have this story. A train is moving backwards at 50 kilometers per hour. If it's at the 2752 kilometer marker, what will it be in 1.75 hours? Here we know that CVPM will work because we're only given one speed, so this thing must be moving at a constant speed. we can get the starting position and the starting velocity from the velocity from the details. In this case, the starting position is 2752 kilometers, and the velocity is negative 50 kilometers per hour. So when we put that together, we have an equation. Now that we have an equation, we just insert the time where it goes in the equation and do some arithmetic. So the velocity times the speed gives the displacement, or the change in position, which ends up being 88 kilometers. When we add the displacement to the starting position, we get the ending position, which is 2664 kilometers. And that's the answer to our question. Another type of problem we can solve with the constant velocity particle model is predicting a time when an object will be at a certain position. This is also about a train. It's moving forward at 45 kilometers per hour. If it's at the 35 kilometer marker at 3 o'clock, what time will it be when it reaches the 327 kilometer marker? First thing we do is use cues from the description to build our equation. In this case, the starting position is 35 kilometers. The direction is forward, and the speed is 45 kilometers per hour. So the velocity is positive 45 kilometers per hour. So the equation is position is 35 kilometers plus 45 kilometers per hour times the time. Now we'll insert the position that we're going to be at the time we're trying to find, in this case 327 kilometers. Now it's just a matter of solving for t. First, let's subtract the starting position from the ending position to get the change in position, or the displacement. In this case, that's 327 kilometers minus 35 kilometers, which ends up being 292 kilometers. Next, we'll divide the displacement by the velocity to find the time. So when we do that, 292 kilometers divided by 45 kilometers for every hour, the kilometers are going to cancel, and our answer will end up being hours. And when we do the arithmetic, we find out that it's 6.5 hours. Now, this isn't the answer to the question exactly, because we were asked to find what time would it be when the train reached the marker, not what was the elapsed time. This equation assumes time 0 at the starting position, but that time was actually 3 o'clock, not 0. So 6.5 hours after 3 o'clock will be 9:30. This is a look at one of the most powerful tools in the constant velocity particle model toolbox, and how to use it in some different situations. Now you'll need to do some practice to get good at it in a variety of different types of problems.